What is going on? Welcome back to another video for partial differential equations. This is going to be our first example on solving partial differential equations. Unlike other videos in the series, this series PDEs, it's much more better for me to explain how to solve these by actually doing examples. And so what we're going to do in this video is we're going to solve a simple PDE, and we're going to be using the separations of variables method, which you probably heard of before, but this will be a different version of it. And so we're going to get started and just solve this PDE. And so we are asked to find the general solution of this partial differential equation between 0 and 1 in the domain of x, and we are given that u of 0t is equal to 0 for t greater than 0, and then the partial derivative of u with respect to x at x is equal to 1 is also equal to 0 for t greater than 0. And so if you recall in our lecture video, there are 4 essential steps to solving a PDE. The first one being is the PDE and boundary conditions homogeneous. And so what that pretty much means is if we let u of xt equal to 0, just everything else equal to 0. And as you can see, if we do, this portion here will be 0 is equal to 0, and then right here 0 is equal to 0, and then 0 is equal to 0. So yes, this is a homogeneous system, and so because it is a homogeneous system, we can go ahead and skip step 2 and go straight to step 3, and it's just pretty much, or not step 3, step 4, and it's pretty much solving the actual problem. And so like I mentioned, we are going to use separations of variables. And so what we're going to do is we are going to let our function u of xt be a combination of 2 functions that we'll call phis of x times beta of t. And we're also going to put the condition that phis of x is not equal to 0 and beta of t is not equal to 0. Because if they're equal to 0, then we're just going to get the trivial solution that the answer is 0. So like, which is true, the general solution, like a solution to this PDE is letting all of this equal to 0. But we don't want to find the trivial solution. We actually want to find a much more general solution. And so, like I mentioned, this is going to be the separations of variables method. So separation of variables, and so you pretty much separate the function into 2 separate variables. In this case, it will be x and t. And so what we're going to do is we're now going to substitute this portion into the pretty much the problem. And so what we'll end up getting will pretty much be getting the second partial derivative with respect to x of phis of x beta of t is equal to the partial derivative with respect to t of, that's rho, phis of x beta of t. And so what we can do now is, if you recall in multivariable calculus, because we are integrating with respect to one function, or with respect to one variable, anything else that is not that variable we can treat as a constant. So for this one on the left side, we can treat phi of t as a constant, and then for the right side, we can treat phis of x as a constant. So we're going to go ahead and take those out of the partial derivatives, leaving us with beta of t times the second partial derivative with respect to x of phis of x is equal to phis of x multiplied by the first partial derivative with respect to t of beta of t. And so now what we can do now is, which is kind of cool, is that because we are now taking the partial derivative of a function, and that function only has that variable that we're taking the partial derivative with respect to, the partial derivatives can actually just become regular derivatives. So instead of partial derivative, the second partial derivative with respect to x, it is just the second derivative with respect to x. And then same thing goes for the other one, which instead of x, it will be t. And we already know how to write those. So what we'll end up getting is beta of t multiplied by phis double prime of x is equal to phis of x multiplied by beta prime of t. And so what we're going to do now is we are going to separate these variables. So we're going to put the x's on one side and the t's on the other. So when we do that, we will be getting phis double prime of x over phis of x is equal to beta prime of t over beta of t. So what do we do now? Well, because we separated these two functions to different variables, these functions, beta and phis, are independent of each other. So phi and beta are independent from each other. And so what that basically means is that we cannot find a variable x such that if we use such that it influences the variable t, meaning that there's technically no way for these two to be equal to each other except if these two are constant. So this equation that I'm about to highlight with a different color. So this equation, phi double prime of, can we make this a little bit more transparent? Phis double prime of x over phis of x is equal to beta prime t over beta t. This is true if and only if they are constant. So what that pretty much means is if these two are each just equal to a constant or just a number. And so what we're going to do now is we are going to let that's supposed to be double prime. We're going to let phi double prime of x over phis of x equal to beta prime of t over beta of t just equal to some constant that we are going to call negative lambda. And the reason why I picked negative is pretty much more on that later. It just makes calculations easier in doing this. And so now what we can do is pretty much just solve these independent from each other, just work with them individually. So we're going to do phis in blue and then beta in orange, not blue. So we're going to start with betas. So if we do beta prime of t over beta of t equal to negative lambda, we can essentially write this as beta prime of t is equal to negative lambda times beta of t, or beta prime of t plus lambda beta of t is equal to 0. And this is why the lambda is negative. So when we put it on the other side, it just becomes positive, which is nice. And so what we have here now is just a simple first order ordinary differential equation. If you want to learn how to solve those, go look at the differential equation video. But when you solve this ODE, the solution that you get is beta of t is going to equal to some constant. We're just going to call it b. times e raised to the negative lambda t. And that's pretty much it. And so now for the other portion, the lambda, not lambda, phi double prime of x over phi of x is equal to negative lambda. This pretty much simplifies to, or can be rewritten as phi double prime of x plus lambda phi of x is equal to 0. And so now what we have here is a second order ODE that again I covered in the ODE video series. And so what happens here is, well, essentially what we get is what this is called a Stern-Liouville problem, which is something that you will encounter a lot in this series. And so I made a separate video on how to solve these with separate cases. And when we solve these, well, I'm just going to go ahead and do just kind of look at the, I guess, cheat sheet, which is the series where I solve this particular problem. We are going to get these different color. Phi of x is going to be equal to some constant sine of x times the square root of negative lambda, where the square root of negative lambda is equal to n minus 1/2 all times pi. And so now that we found the solution for phi of x and b of t, we know that u of x, different color, u of x is u of xt is equal to phi of x times beta of t, which is equal to b sine of x square root times the square root of negative lambda times e to the negative lambda t times b. And so what we can essentially do is just convert all these into just a single constant, which we're going to call a, lambda of t, where the square root of negative lambda of n is equal to n minus 1/2 times pi. And so defining what our square root of negative lambda is, that means there are multiple or infinitely many solutions to pretty much our phi of x. So that means our actual general solution for this problem is the sum from n is equal to 1 to infinity of a of n sine times x times the square root of negative n multiplied by e times negative lambda n times t, again, where the square root of negative lambda n is equal to n minus 1/2 pi. And if you look at the cheat sheet video about this portion here, this statement is only true for all n being positive integers. And so yeah, that is pretty much our general solution. And that is, yeah, that is it for this video. We found the general solution. As you can see, we haven't plugged in the boundary conditions. because that will pretty much give us like a particular solution. So in the next video, we are going to continue this example and actually find the particular solution, which means we have to use the boundary conditions. But other than that, this is our final answer. And so hopefully you can see how useful this method is as we make a PDE and break it down to 2 ODEs that we can solve, and then just put them back together and giving us this solution. So hopefully you guys learned something, and then I'll see you guys in the, I guess, part 2 of this example. So yeah, I'll see you in the next video.